Hi everyone, I'm Yulia. I'm a developer advocate at Vonage, previously known as Nexmo, and I will be your host for the rest of the day. So without further ado, let us present the next two speakers we are having today, Avner Tamir and Opher Dubrovsky of Nielsen. And we are going to find out more about the magnificent beast that is serverless and how we should go about taming it. So guys, let's give it away.
Good morning, good afternoon, everybody. Let's share our slides and we'll get started. Okay, so we're going to talk about serverless and specifically why it's such a beast of a technology. We'll talk about the amazing powers you get with it, some of the pitfalls, and how not to get burnt while using it. I think you love to hear some of our stories that we actually did get burnt, but we learned a lot by doing this. So to tell you all of this, we'll talk about a system we built called Data Out. It's a big data pipeline we've built entirely over serverless. It runs a crazy number of events per day, which top day ever, we've had 250 billion events a day. We still scratch our heads every time we look at the metrics, and it's all running on serverless. So before we start, let's explain who we are. My name is Opher Dubrovsky. I'm a big data dev lead at Nielsen Identity Engine, and I love data and challenges. And with me is...
Hi, my name is Avner. I'm leading the cloud operation team of Nielsen Nielsen Identity, and I just love to automate everything and remember this.
Yeah, and Avner and I have been through this journey for a while together, so that we have a lot of lessons learned to share. Some about us.
Yeah, we're, as I said, Nielsen Identity Engine. Originally, we're a startup called Exolate, been acquired by Nielsen 5 years ago. We're a data company. We collect lots of data, as Opher mentioned earlier. And from this data, we build models for insights, for marketing, for campaigns, for business decision. In the ad tech industry, for those familiar with the industry, it's called the DMP, what we're doing over there. Our infrastructure is running on AWS. We're paying something like $500,000 a month to AWS for that. Part of it, which is also relevant to our current talk, is that we're running something like 3,000 nodes, sometimes more, something less, for Spark on a daily basis. And we collect something like 300 billion events a day on like the 250 billion that Opher mentioned earlier. On top of that, there's other data going on around the system, which is not part of what we're going to talk today, which sums up to something like 60 terabytes of data that we collect on a given day. So we're going to, as Opher mentioned earlier, we're going to talk a little bit about the serverless, about the architecture, about how good this architecture is, the problem, the solution, the problem that we have with this architecture, the solutions that we found for it. And afterwards, we're going to talk about a bit of the pitfalls that we had, and how we solved them, and how we managed to continue to progress with them. And at the end, we'll leave some time for Q&A.
Cool. So let's start with serverless, just to put everybody on the same page. I'm sure some of you already are familiar with it. But let's do a quick intro to it. So originally in the past, developers would write code, and then to be able to run it, you needed to deploy and install it on some servers, start them, run them, and then over time you'd need to maintain. In cases that you had a lot of data, you needed to scale them up. So that was a lot of work as well. As developers, we really care just about running the code we wrote. So all the rest is just a hassle. So there's lots of hassle around it. And obviously with the hassle come a lot of costs. So there's hassle and cost. Then comes serverless. So serverless, basically, it lets you as a developer just focus on writing your code. And then just deploy it and run it on serverless. And the infrastructure takes care of all the rest. So the nice thing about it is that all the difficult part you had around your system, you no longer need to take care of. you can save money, and I'll explain a bit later why that is true. Obviously, there's less management hassle. You no longer need to install machines and maintain them and update them. Scaling, which is something we use a lot in our system, is automatic out of the box. You don't need to do much. It just scales up and down as needed. And another part of it is it's highly parallelizable. So which means if I have a lot of jobs that I need to run, I can just spin up more serverless instances and run them in parallel, which is great if you need to deliver an SLA to your customers, because no longer do their tasks need to be stuck in some queue waiting for your resources to free up. You could just spin up more resources in parallel. And we've used this extensively throughout different systems that we've had. The unexpected benefit is cost reduction. This is a bit counterintuitive, but the great thing about serverless is that you're actually paying by the second for the amount of time your code runs. So that means if you can improve your code and make it run faster, that immediately translates to cost reduction. If you can improve your code by 20%, you get a 20% reduction in cost. If you can improve it by 50%, you get a 50% reduction of cost. This is great, and this is something we've never had before. In the past, when I was improving my code, the servers would just be not busy and run more lightly, but I was still paying for the server. And here, it immediately translates to cost savings, which is great. In our system, when we started out, we were paying something like $7.50 per billion events that we processed. Over the last year, a little bit over a year, we constantly drove the cost down. We're at a point that we're paying $4.2 per billion events, the same amount, the same type of events. So we're almost at the half point of the cost we started with, and we are still going. So I think eventually we'll probably get to something like $2, which is amazing. So a bit about our system. So our system is, we call it data out. It's a huge data pipeline, as you've seen before, with the amount of events we process. And it basically takes all the marketing data that we generate and constantly uploads them to the ad platforms that are partners of us. Ad platforms are basically any platform that you could, as a marketer, go to and run campaigns to customers over it. So platforms like Google, Facebook, Snapchat, Twitter, TikTok, stuff like these are all ad platforms, and all of them are partners of us, and we constantly upload data, segmentation data to them. So the goals when we went to build the system up were we needed a big data pipeline that's running 24/7, sends all the data I mentioned to the ad platforms. It needs to support a lot of different platforms, so it needed to be very flexible. Each platform has its quirks and requirements, so we need to pretty much take the data that comes in and transform it to the specification of the platform, and then also format it in the way they would like to get the data. We have about 400,000 segments and millions of users. So on a normal day, we get about 120 billion events a day that we upload. Obviously, I mentioned the 250 billion events previously. That was the top day ever. We'll talk about it a bit later. We also needed the system to be highly scalable, very cost effective, because obviously when you're running so much data, this could get really costly. Needed to meet SLAs, so we wanted to make sure that when data comes in, we process it within a certain amount of time, no more than that. And transparent, because we needed a lot of metrics. We needed to know the data is flowing to every platform. And if there are issues, if the system is running but some of the platforms are not working, we needed to know of that immediately. So what was our solution? Our solution was basically building something that's totally serverless. This is the way the system looks. On the left side, we have files coming into an S3 bucket. And then they are picked up by the system. They go through the system through 2 stages and then are delivered on the right side to the ad platforms. So the left side basically picks up the files and does loading and transformations on the data. It arranges the data for each of the different platforms according to its specifications. The right side is what manages the delivery, and that is actually picking up the files and sending the files to the different platforms, depending on their authentication and protocol requirements. The left side is running on a containerized Spark workers that we've actually put Spark in a container, and we're running it on pods in Kubernetes. This is not to be confused with Spark over Kubernetes that that is now in the works. We're running separate Spark, little mini Spark clusters in each pod, and we scale up and down by firing up more Spark containers or pods or taking them down. And then on the right side, we use AWS Lambda infrastructure to basically send each Lambda function a bunch of files it needs to deliver, give it a target, let's say Google or some other platform, and then it will deliver the data. There's also some databases there that keep track of everything and count up the metrics and see our success rate and so forth, but it's less relevant for this talk. So what makes serverless so attractive for us? As you could see on the bottom, data comes in over the day and it goes up and down over the different hours of the day. What's really nice about serverless is that the amount of Lambda functions we run, the serverless infrastructure basically can scale up and down with the data that comes in. So that's great because when we need more capacity, it'll immediately scale up and we'll have more and more functions. Top hours that we run, we can get to something like 3,000 or 4,000 concurrent Lambdas that run in parallel. And then the minute we don't have any more data to send, it immediately scales down, which means we're not paying for it. Obviously, the costs go up and down with it as well, but that's also an opportunity for cost savings. And the reason is, if you look at classical server systems, usually people used to design them for the worst case scenario. So if you have a peak in the day, you design your system capacity to be close to that peak. Maybe you're willing to tolerate some delays, but so maybe it doesn't handle the fullest of the traffic during the peak, but close to it. And then what happens during the rest of the day, it might be underutilized. So usually, if this is a road in rush hour, usually there are lots of hours in the day that the road actually looks like this, which means that you are wasting a lot of money. And as we got into serverless, we realized how much that is, because this was something that was really hard to analyze before. So back to our example. So basically, as data comes in, the infrastructure goes up and down with it and breathes basically with it. The costs go up and down, but the savings are all the area that is in purple here. Basically, if we had designed a system, a comparable system to handle the peak load, we would have paid additionally all the purple area. So this is really great and an amazing feature for us. So let's summarize this and then jump to some of the pitfalls we ran into. So the benefits are scale up and down really easily out of the box, not a lot of work to get this going. Run in parallel, we could just parallelize everything. Again, that's related to scale, and we can guarantee our SLAs. We save money when we're not using it. We also save money when we are able to optimize our code. So over time, we can gradually drive the cost down, and it's simple to maintain, I guess, in a nutshell, because as you will see, there are other difficulties that trade-offs that you get with that. So what did we really get? We got superpowers, right? Because we have a system that can scale up and down with amazing superpowers, but with superpowers, you also have to be careful, and you'll see in some of our examples the flip side of superpowers. Some numbers on our system. So as I said, a normal day, we have 120 billion events. highest day ever. We had 250 billion events. During that day, we processed 17 million files with 55 terabytes of data. The interesting thing is the system over a normal day scales up and down between 1 and 6 terabytes a day. So it's actually going up and down over the day, and the system adjusts to fit the data. You can see on the right, this is a graph of an average day of how the data actually looks. But, so as I said, life is not that easy. Everything seems rosy when you see the brochure, but when you dig into the details, there are all kinds of pitfalls that you have to avoid. So with that, let's go into some pitfalls. Avner?
Yeah, the first pitfall we had is what we call the clash of clans, is that we had a system at the moment which was created, which was great, it's been working, everything was done, everything can be done any moment, can be changed, change can go into the system and out of the system every time. The problem that comes with it is that it was open and there was too many hands working in parallel, too many people doing things of their own things of their things tend to change, to break. We had a situation where there was a problem at night and the developer pushed a change to some configuration and pushed it only to one region of AWS and not to others. And we had so many other moving parts in the system that had been affected by any change. And there were many hands working on it in parallel, developers, data engineers, the cloud ops, etc. And there was no way to manage everything all together. So we started to look for solutions. How are we going to do it? First solution was the classic IT solutions. We have problems, we block everything. That's how we work. And we started blocking everything. Now everything should go through our cloud ops team. Everything should be approved, etc. And that created a lot of tensions and that caused the cloud ops team to become a bottleneck. And as much as we like to block things, we hate to be a bottleneck. And we tried to find, and they created a lot of tension and argument between the engineering group and the cloud operations group because it was a blocker and everybody was waiting for the cloud ops, etc. And it created a lot of tension and arguments. And we said, okay, so this solution doesn't work. Let's look for another one. And the second thing we thought about was to automate anything and everything that we can. And as I said earlier, I just love automation. That's what we do. Our idea was to give developers access to run all automation tools. And the concept, and it is something which is also something we do anywhere in the Nielsen Identity Engine. We like to empower developers. We like to give developers the tools that we trust our developers to manage production and to do things by themselves, and not to have too many blockers on the way to do it. So that was our plan, to give the developers access to run all the tools, and the goal was to reduce tension and that everybody could work with it. So what we did, we created a peace conference. We took developers and we took the cloud ops team, cloud ops representative, put them in the same room and told them, guys, you're not leaving this room until you come with a holistic solution for everything that we need to be done to maintain this technology and amazing tool that we're having here. So what happened was that for, I think it was 2 or 3 weeks, a bunch of engineers were working together for almost 12 hours a day in the same room. We kept on providing them with foods and other stuff to keep them busy, keep them in the same room. They were working there for for 2 or 3 weeks, and until they came with the holistic solution, which includes all the tools they need and all the processes and the deployments. We're now running everything over there based on Terraform, for example, we decided the decision was to take Terraform to manage the infrastructure, Jenkins to orchestrate it. We have CI running on every change going into the system. We have CD when we talk production. We introduced the concept of canary deployment to our big data system, which was new. We also started working with the gradual deployment. And of course, we have the ability to run a full deployment, which led to a new era, which is where we are for the last year or so. The developers own production. They do deploy whenever they want. They can deploy what they want anytime they want when it comes to their code changes. The only place where the cloud ops are still involved in deployment and when there is a configuration change, something which might have impact on things which are outside of developer scope, such as ports, changing, if you need something which requires some more AWS experience, as I said, port or VPCs, etc., stuff like that, that still go through the cloud ops to approve and to change, and we still maintain the tools, or if there's a need for any new kind of infrastructure, that's where we're still part of it. So that was, I think, one of the biggest pitfalls we had on the way, and moving back to Opher to some other problems we had.
Cool. So let's talk about some other stuff we ran into, and that is cost. I think everybody likes to talk about cost, and especially hear about some goof up issues that happen. So as I mentioned before, optimization will actually save you money, right? But if optimization saves money, I guess the reverse of optimization will cost you money, right? What is the reverse of optimization? It's called bugs. And we had a few bugs that were very, very costly. I want to mention two of them, and I'll tell you the story about them. So one of the first bugs of interest is there are reprocessing bug. So the way, since everything is working in parallel, we had to find a way that once in a while a task gets stuck and does need to be reprocessed. The way we did that is we have a monitoring a Lambda or a service that monitors the tasks and checks how long a task takes. And obviously, if it goes on for too long, we decide that something has happened and we should reprocess it. We have a threshold, a reprocess threshold that this Lambda checks. And if the task goes over that threshold, we set it for reprocessing. So what happened? So we were working on some code improvement. One of the developers manually set the threshold to a higher threshold to make sure stuff doesn't get reprocessed. But the next day, somebody deployed code using the automated CI/CD, and that overwrote that threshold back to the lower value. As a result, what happened? So the value went down. Because the value went down, a lot of additional tasks were basically marked for reprocessing. So as you can see, we had these two purple, in my example here, two purple tasks that were set for reprocessing. After the threshold reduction, we had lots of tasks that needed to reprocess. We got to a point that some of the tasks got reprocessed 38 times. If we look at our costs, so we had like 3 days of increased cost due to that. We caught the bug within a day, but after we stopped traffic, we then had to go back, fix it, and reprocess traffic. So you can see there's an uptick in the cost again. This is a view to the AWS Cost Explorer of our system. You could see here in purple that Lambda costs are skyrocketing. This is in thousands of dollars on this graph. The total cost for this bug were, for these days, the total cost was $7,400 on these days. On normal days, 4 days like these, we usually paid about $4,000. So the damage was $3,400 just for a little bug. That was our damage. The solution. So basically, if you think about it, Avner talked about all these wonderful CI/CD processes, automation, and all of that, but we actually basically went over our own procedure and manually changed something. So we decided we're going to get much more hardcore about not doing that, and anything new that needed to be included in the automated processes should be automated into them and obviously not be done manually. The other thing that we decided to do is introduce task validations. So instead of a Lambda getting a task and running it, it would actually validate it against some other parameters. So we added some validations around with timestamps to check if a task basically was assigned and by the time the Lambda got to process it, it was already modified by some other task, we would actually drop it and not process it. So we had like a two-stage or two-factor validation before running a test. So in this case, now that we have validations, if we ran into the same problem that we had before, the Lambda would wake up, see that the task is not valid anymore, and just go back and complete and not run the task. So that would have saved us a lot of money had we had it in place. Bug number 2, Lambda throttling. So this is, again, something that came out of left field, unexpected. This is the way our workers, dispatcher workers, work. There's an SNS that calls a Lambda that we use to manage all the tasks that needs to be done. It looks up in the DB and decides which tasks need to be dispatched. It then packages a few of these files into a task and sends it in a fan-out architecture to the workers. So each work manager can invoke hundreds of workers in parallel, and this is what gives us the scalability of the system. But what AWS also has, it has a concurrency value on a Lambda that you create, where you can prevent too many Lambdas to work in parallel. So on our work manager, the concurrency was 1, which means that only one can work in parallel. You cannot wake up or invoke another one before this one completes. What happened is over time, the amount of data grew, and we needed to create more work managers. Our system does that automatically, but the concurrency was set to 1, so it tried to invoke more work managers, but they did not wake up. AWS has a throttle queue where if the invocation fails, it would keep the task in a queue and then try some exponential backoff and resend the task again later on. When we realized we are not processing all the work that we had because the amount of data grew, we decided, okay, so let's open the concurrency up and just allow it to spin up more Lambdas. We did not limit it. We just opened it up and set it to unlimited. And because we didn't realize there's lots of waiting tasks in the throttle queue, the minute we did that, we got a lot of requests for new work managers. We ended up at one time, we had like 100 of them running in parallel. And each one would get tasks from the DB and send to the workers. Because they were running at about the same time, some of them actually got the same task from the DB and send the same task over and over to the workers. We have a mechanism to prevent them from working on the same task, but at that time, due to the unexpected nature of this, it did not actually work for this scenario. So what happened was that we got hundreds or up to 100 work managers working in parallel. And due to the fan-out architecture, we started out with a little amount of workers, ended up getting a lot of them. This is how the cost report on AWS looks. You could see this, in this case, it went for 5 days. The first day we realized we have an issue pretty quickly. It took us a while to figure out what's going on. It was not really obvious what's going on. You could see that the cost went down a bit because we stopped processing certain things to prevent that and then had to reprocess again on the 4th day and 5th day. The cost, the damage was $2,500. Again, total cost for these 5 days was about $6,000. Average during that time was about $3,500 for these days. So the delta is $2,500 of damage. And believe me, this is really painful when it happens, and you have to really tell everybody this is what happened and feel really bad you're wasting money. The solution for this is basically new monitoring and alerts. In our case, it's on the number of invocations. So we set up alerts on invocations of the work manager Lambda, and in total, if the invocations go up suddenly, we really want to see that, especially if they spike up quickly. And the other thing, which is not that obvious, is that the cost explorer in AWS is updating once a day. So usually it takes like a day and a half until you see the actual cost of yesterday. By that time, it's too late with a system like this. By that time, you could have blown through thousands or tens of thousands of dollars. So we started building real-time measurement of the cost. As I mentioned before, the costs are related directly to the processing time of the Lambdas. So we started measuring and reporting the measuring time, the processing time of each Lambda. And we're in the process of setting up alerts and dashboards on that. So we could, if there's a spike up in costs, we'd be able to track it and be aware of it within minutes. Pitfall number 3. So we talked about costs. We talked about some of the process problems we had with CI/CD. Let's talk about number 3, which is DDoS attacks on partners. So as I mentioned before, the great thing, and that's why I called it superpowers of our system, is that it scales up and down as traffic comes in. Remember that slide? That's wonderful. The problem is the world does not work like that. So a lot of the partners that we work with have a bunch of servers that just sit there and get the data we send them. So even though we can handle any amount of traffic you throw at us, we get 10 times the traffic, we'll process it. Most of the world does not. So one day we get an email from a partner saying, guys, you're killing our systems. Please check. Is there anything you're doing? Let's get on a call. We got on a call with them, and they explained that we're basically crashing their servers. And we started checking, and we realized that the data for them was going up and down about 6x over any day. And usually it was not even gradual. So when we had some peak hours, it could jump from like 1 to 6 times 1 within a matter of minutes. And that was really killing them. We sat down, we started analyzing this. We realized this is not a problem of them. This is a problem of a lot of systems. Even some of our bigger partners can handle any amount of data. We've noticed problems in certain cases. So we decided to implement a throttling mechanism. You have to realize that basically the only reason we need throttling is because we have such superpowers. If you look back at the Hulk picture I showed you, the Hulk is great, right? But if the Hulk needs to do some really minute operation, he's got too much power for that. So this is what throttling was aiming to solve. We developed a throttling mechanism internally in the system that can throttle on pretty much anything we ran into. So today we can throttle on megabytes per second, items we send per second, HTTP requests per second, HTTP connections per second, and we can extend it to anything else that we'll run into in the future. And that pretty much solved our DDoS of partnering problems. Okay, so let's summarize what we went through and how to avoid some of the pitfalls. So I think the main thing is you really want to measure all your risk dimensions. So risk is, in our case, cost is obviously a risk. You want to measure this. You don't want to rely on some report that you get once a day. Another risk we have is flooding partner systems. So you want to measure that. You want to set up alerts on these as well, which we have. The risks in our system are basically cost, throughput, and load. In your system, the system you build, it might be something else. So try to analyze what it is and measure it and set up alerts, because this is so quickly happening and scales up and down so fast. You want your alerts to be quick. You want to get an alert within minutes of these high level and high impact events happening. You want to build really detailed dashboards. So after we got alerts, you want to be able to investigate quickly what's going on. The more dashboards we built, giving us slicing and dicing into what's going on in the system, the easier it got. In the beginning, when we set up this system, it took us sometimes like 2 to 3 days to figure out what's going on every time we had a problem. And then usually like 3 to 4 days just to fix it and recover the data. That was horrible. So we built dashboards. The goal was that you'd be able to figure out any problem that comes your way within 5 minutes, and then within another 5 minutes fix it. So we built a lot of dashboards and thought up of all kinds of metrics. And we also built tools to help us fix problems. So usually when there's a problem, we had to reprocess some data. We have tools for that. Now reprocessing is just a few clicks of a button. In the past, it used to be somebody had to write code and spend a few days just trying to reprocess stuff. And then maybe the last thing I'd recommend is build circuit breakers in the system. So if you want to stop your system, you want to be able to hit a button or click some button on a page that stops all the system in case you need, or stops parts of the system when you need to do that. And then maybe a little summary about serverless. I think as you saw, you get amazing powers and scale. It's great for optimizing and reducing your costs over time. You get basically on a downward trending route if you are minded into that, and you can work a lot of your data in parallel and process it in parallel, which is amazing. But as you saw, you want to be aware of escalating costs and be very careful with it. And I would summarize, be ready for the unexpected. With that, we can move on to any questions if anybody has any, and I'll stop sharing the slides and we'll move to questions.
Yes, we have quite a few questions. Thank you for that presentation. It was amazing. So why did you choose to put Spark on Kubernetes instead of using AWS EMR?
That's a great question. We actually started with Spark on EMR, but we realized that a lot of our data is basically, we send data to platforms. So the data is partitioned by the different platforms. When we were running on EMR, we had a big cluster running a lot of chunks of small data, and that made it really hard to optimize for costs. If you recall, we were trying to optimize everything to be as cheap as possible and really efficient. Because of the big cluster, it made it really hard because first the data changes over time, and EMR does not scale up and down really quickly. I mean, you could scale it up and down within minutes, but we are talking about seconds. We want to scale up and down within seconds. And second, because the data is not partitioned well, we had to repartition, and that included a lot of work, added a lot of work for us. So instead, we just created our separate small EMRs. They give us all the flexibility of basically Spark SQL, so it's easy to write the transformations without adding any code. Our solution guys do it themselves. And we could scale easily up and down and actually optimize to use all the resources to 100%. Maybe one point in that, when we used to go into Ganglia before in the EMR, you could see that a lot of the time it was not really working hard. It was like idling at 30–40%. Now we could optimize each pod to run close to like 95% CPU, which is great. Next question.
Thank you. All right. So did you use any frameworks for automating deployments, or did you choose to use custom scripts built by you? And why did you choose to go that path?
We went with the Terraform project that we wrote to meet our specific needs. Actually, I don't think we looked a little bit and we didn't find anything open source kind of template, that something that looks similar or close to the volumes that we had to deal with, the complexity we had to deal with, and we decided to build our own Terraform project for that. And also we built it gradually. So we started with a small, started small with one region, and then on top of that added more and more things as it goes up. So it was very easy for us to build it like that, like gradually to build it.
Thank you. So what solution did you use for collecting metrics or audit data, and how did that impact your costs?
So that's a great one. We started out with Datadog. We have a lot of dashboards on Datadog. I think it's a great solution. one of the problems we had is that you pretty much have to set your metrics in advance. So you cannot, so if you recall, we have about 200 platforms, and there's another sub accounts on the platform. So we ended up with about 500 different entities we upload data to. With Datadog, you can only hard code the metrics for them. So one of the challenges that we couldn't figure out to do there is to do kind of like a group by the different platforms, so we can see the data traffic for each one. So that was one of the challenges. The other one was that some of our organization has been moving to Prometheus. So right now we're in the process of moving some of the metrics to Prometheus, and some of the metrics we put on a superset, because in superset we can run any query we'd like against a database. It's not as nice as a Datadog that gives you everything, just send a metric and everything is done for you. But on the other hand, it complements some of the stuff we wanted to do, like the group by option. So right now we have Datadog and superset side by side, and slowly we're also adding Prometheus. Sorry that it sounds complicated and it's not like a simple one-shot solution, but that's kind of like our situation. I think over time we want to integrate everything into one solution. And not run multiple things in parallel. Yes, next.
Thank you. Thank you. And we have time for one more, which is, how did you throttle the output of your service, and how did you architect the control of these throttle configurations on a per customer manner?
Okay, that's a great question. We spent a lot of time on that. One of my developers actually gave a talk about that a while ago. It's a complex problem. Right now, what we did is we have we adapted the work manager Lambda, the one that actually assigns all the tasks, to be aware of how much of the throttled metric is actually being processed at the same time. So when I say throttle metric, think about, let's say I'm uploading data to some platform and the limit is 250 megabits per minute. So we introduce metrics that measure that per each second. And then the work manager Lambda, every time it needs to assign files to send, checks how many files are actually being processed right now, does a summary of how many megabits per second that means, sees how much free capacity is left, and sends more of it. So this is the way it works. It's working great. Notice that it's a push model. I think going forward, we want to move to a pull model. So we're thinking of changing this architecture and using tickets, like if you're familiar with Kanban, where we have like some queues of tickets for each throttle entity, and every time a Lambda pulls the next task, it sees how many free tickets are available, or basically resources available, and that's the way we could limit it. So that's our future plan, and the way it works now is with the push model I described. Hope that answers it. Maybe in the future we'll do a bigger talk about throttling, which is a whole complex topic in itself.
That would be amazing. Thank you both. It was a really great talk. Now we're going to go on a break for 5 minutes. I would like to ask everyone to go back in My Connector and select the next session, which is going to be 100 machines do 100 job in 1 second by Roberto Freato. See you all there in 5 minutes time.
Bye.
Bye.